Our project is done using Raspberry Pi Pico, which is powered by RP2040 microcontroller chip at the center. And for the input, we use this rotary encoder, which provides rotational data through its clock pin connected to pin 5 and the DT pin connected to pin 6. Next, the output is shown in this 16:2 LCD display. And to minimize the wiring, we have connected this to the I2C module, where the SDA data line is connected to pin 8 and the SCL clock line is connected to pin 9. And finally, we have the two LEDs to display the Morse code. The top green LED is connected to pin 16 and it is for the dash part of the Morse code. And the bottom red LED is connected to pin 13 and it's for the dot part of the Morse code.
Now let's jump into the code. The class LCD API is an abstract based class which is used to provide the common functions for character LCDs. The constructor is used to store the LCD dimensions and track the cursor positions. So the clear function is used to clear, move function is used to move the cursor to a certain position, put character is used for uh, placing a single character of the string, and put str is used to place the string in the LCD. This is the main method for displaying the full string. So the first part is to display the full string according to the cursor positions we choose or like automatically set, and the else part is for placing if another string is there and we need to place both, and we are using this one. Now let's go to the I2C LCD Pi. This class extends LCD API and implements LCD operations using I2C protocol, since we are using I2C module LCD. Now the class LCD I2C LCD is used for defining the LCD control bytes, and here the constructor is used again. It initializes the LCD with I2C details and dimensions and stores the parameters and calls write init function to prepare the LCD. Now the write byte sends a string to LCD with backlight on, and pulse enable creates the pulse to latch data in LCD. Uh, Send function sends the 8-bit data in 4-bit chunks, and write nibble is used to write 4-bit nibble and triggers enable command function. Write command is used to send rs equals to 0, and write data is used to send rs equal to 1. Now we come to write init, which follows the LCD init sequences, sets 4-bit mode, and we configure the function and turn on display and clear the screen and sets to entry mode. Now the clear function is used again to clear the screen and wait for the function to finish, and we use move to change the cursor position and put character to place the character in the LCD. Now coming to the main.py, so machine.pin and machine.I2C is used for accessing GPIO pins and I2C hardware. So utime is used for providing delays. Sleep is used for standard second delays. And from the ICD I2C underscore LCD file, we have imported the I2C LCD class which controls the LCD, and we have defined the messages which will be the inputs and the Morse code dictionary. Now coming to the function, so Caesar is one type of the cipher we use here, and it basically increases the shift. So shifts the number, the value or number based on the shift value we provide. Since we have fixed the value as 3 here, so it just if we give the value as A, it just gives the value as B, and ROT13 is just adds 13 values to the input. So it will be very easy to decrypt from it by just subtracting the value, and our Vigenère cipher is based on a keyword, and it repeats again and again depending upon the number of letters in the input we give. So it shifts based on the keyword we give here. We use code here. Now this LCD underscore show is used to clear the lines of the LCD, and it uses the functions in the LCD underscore API which we have discussed earlier, and display step is used to call the LCD and wait for 3 seconds to let the user view the stage, and blink Morse is used for blinking, showing the Morse code output in LEDs. And now we set up the pins, and the index is given as 0, and we have this we use for the rotary encoder. And now we'll just select the message, and the message will be shown. We have to select by rotating the rotary encoder, and it will get selected after waiting for certain time, which is 5 seconds. And since we have fixed the shift as 3, the shifts the encryption starts, and it will be shown in LCD. Similarly, the decryption starts and it will be shown in LCD, and finally the output will be shown in the LEDs. So that's it with the code.
So the primary step for our project would be to set up our target device.
When we connect the Pico by pressing the boot cell,
the target system would already be selected. So what we need to do is just select our variant of our device, which in our case would be our RPi Pico. So it's important to remember that we need an active internet connection for this process. So we need to wait, we will just wait until this installs. Okay. So the next step in our project would be to select our input message. This can be done with the help of a rotary encoder. Let's say we take the input message as call home. Yeah, we will take that. So our program is designed to jump by each step with the interval of 5 seconds. So if the message is call home, first it will be encrypted by a Caesar cipher, and then by our ROT13 cipher, and then by our Vigenère cipher. And the output of our Vigenère cipher is now being decrypted by the same Vigenère cipher, and by the same ROT13, and by our Caesar, which will get the final result as the same input message. So the outcome of our project is to show the Morse code. So the Morse code can either be represented by a buzzer or LED, and each blink in our LED represents a dot or a dash depending on the color of the LED. So the pause timings between each LED are like 0.2 seconds between letters and 0.8 seconds between the words.